Okay, let's dive right into this. Welcome to today's Explainer, where we're going to trace the absolutely fascinating evolution of real numbers. We're taking a journey that starts way back with ancient humans scratching tallies into bones and takes us all the way to the infinite, unbroken continuum of the number line that we use today. Because, you see, mathematics didn't just pop up in a sterile classroom. It was born out of pure, everyday human necessity.
So, here's our roadmap for today. We'll kick things off with 1. The dawn of numbers. Then we'll move into 2. Integers and arithmetic laws. Explore 3. The rational number line. Zoom in on 4. Absolute value and density. And finally, we'll wrap up with 5. The Explainer Master Quiz.
All right, Section 1, the dawn of numbers. Let's take a look at counting primes and how early humans actually birthed the natural numbers.
Imagine living thousands of years ago near the Saraswati River. To make sure absolutely no cattle wandered off, early humans used this brilliant simple system called one-to-one correspondence. You drop a pebble in a pot for every cow that leaves, and you take one out for every cow that returns. That simple, practical act right there, that birthed counting. And we actually have physical artifacts proving that this abstract concept of a number is tens of thousands of years old. Long before any decimal system, people were carving tally marks into bone. We've got the Lubombo bone from southern Africa dating back 35,000 years, which was likely a lunar calendar. Then, around 20,000 BC, the Ashango bone pops up near the Nile River. And then, jumping way forward, we finally get the formal definition of zero in 628 CE.
Now, I want to zoom in on that 20,000-year-old marvel from the Democratic Republic of Congo, the Ashango bone. It's covered in these distinct columns of asymmetrical notches. But here's the crazy part. It's not just random scratching. No way. One column literally demonstrates multiplication by 2. It's doubling. And another column? Well, it contains a specific grouping of tallies that is, honestly, gonna blow your mind. Let's test your pattern recognition real quick with our first question. Think about this specific sequence of notches grouped on that bone. 11, 13, 17, and 19. I want you to actively think about what mathematically links those specific values together. And based on that rule, what would the next 3 numbers be? Take a quick second to chew on that.
Got it? They are prime numbers, specifically the prime sitting right between 10 and 20. This absolutely proves that ancient humanity recognized prime numbers, values that are only divisible by 1 in themselves, way before modern mathematics was even a thing. Following that exact pattern, the next 3 primes would be 23, 29, and 31. Pretty incredible, right?
Okay, Section 2, Integers and Arithmetic Laws. Let's see how the rules of arithmetic came together.
For millennia, the number line just started at 1. If you had 5 apples and gave 5 away, you were just left with, well, a void, nothing. But over in ancient India, philosophical traditions were deeply pondering this idea of emptiness, known as shunyata. Inspired by this profound comfort with nothingness, a brilliant mathematician named Brahmagupta transformed it into a fully operational number in 628 CE. He formally defined 0 as the exact result of subtracting a number from itself. Literally overnight, 0 went from being a blank placeholder to a foundational pillar of math.
And Brahmagupta didn't stop at inventing 0. He essentially gave us the foundational arithmetic laws we still use every single day. He established that adding 0 leaves a number perfectly unchanged. But his true stroke of genius? He formalized negative numbers by thinking of them as debts and positive numbers as fortunes. Because of that, he was able to boldly state that the product of 2 debts is a fortune, which, if you've ever wondered, is exactly why a negative times a negative equals a positive.
Which brings us to question 2. In math, a set of numbers is considered closed under an operation if doing that operation always spits out a number from that exact same set. Now we know natural numbers are closed under addition. A positive plus a positive is always a positive, for sure. But are they closed under subtraction? Think about what happens if you have 5 apples, but you somehow try to give away 10.
Right, so the crucial takeaway here is that natural numbers are absolutely not closed under subtraction, because 5 minus 10 leaves you with a debt of -5. So to fix this broken system, mathematicians had to expand their universe. They created the set of integers, which we denote with a z. This whole new set seamlessly combines positive natural numbers, their negative counterparts, and 0. And just like that, subtraction finally becomes a closed operation.
Moving right along to Section 3, the rational number line. Let's talk about representing parts of a whole.
As civilizations like the Indus Valley grew way more complex, inventing standardized weights and measures for trade, just counting whole items wasn't going to cut it anymore. People needed a mathematical way to represent parts of a whole, like dividing a field equally among siblings. Enter the rational number, denoted by a q for quotient. A rational number is just any value you can express as a fraction, p over q. The rule is both p and q have to be integers, and critically, q can never be 0. We also assume they're co-prime, meaning they share 0 common factors other than 1, just to keep things in their simplest form. On our trusty number line, you represent these by simply dividing the space between integers into q equal parts.
And remember Brahmagupta? He brilliantly extended his arithmetic laws right onto these rational fractions. He set up rules for equality using cross-multiplication. He made sure these fractions perfectly followed the commutative law, meaning the order you add or multiply them doesn't change the answer. He established the distributive law. And most importantly, rational numbers are closed under addition, subtraction, multiplication, and division. Well, except for dividing by 0, of course.
Let's actually put these rules to work with question 3. Picture a merchant in the ancient trade city of Lothal. He's exchanging spices for copper ingots, and the going rate is 15 ingots for every 2 bags of spices. So, if he brings exactly 12 bags to the market today, how many copper ingots is he going home with?
By using the arithmetic of rational numbers, we just set up the fraction 15 over 2 and multiply it by his 12 bags. Now, because rational numbers don't have just one unique representation, we can scale equivalent fractions up or divide out common factors completely seamlessly. Half of 12 is 6, and 6 times 15 gives us 90. So he leaves with a very solid 90 copper ingots.
Section 4. Absolute value and density. Let's look at the hidden spaces living between the integers.
Okay, let's do a little zoom-in visual metaphor on our number line. First up is distance, measured using absolute value, which is written as x wedged between 2 vertical bars. Absolute value is simply a number's pure physical distance from 0 on the number line, completely ignoring direction. It doesn't matter if you're moving left toward a debt of -5 or right toward a fortune of +5. The absolute physical distance you traveled is just a flat non-5.
And that perfectly sets up the concept of density. Think about literally any 2 rational numbers on your number line. It doesn't matter how unbelievably close they are. If you add them together and divide by 2, finding their exact average, you are always going to find another valid rational number tucked perfectly between them. And because you can repeat that process infinitely, it means there are literally infinitely many rational numbers densely packed between any 2 points. It is absolutely mind-bending.
So, let's lock in Brahmagupta's logic one more time with question 4. Mathematically, 10 minus -5 equals 15. Now this rule trips everyone up. I want you to think about why subtracting a negative number is exactly the same as adding a positive number, but use a real-world example of debt to explain it.
Think of it exactly like this. Let's say you've got 10 rupees in your pocket, but you also owe your friend 5 rupees. So you have a debt of -5. Now, if someone comes along and subtracts that debt, meaning they just take the debt away and forgive it entirely, your net worth essentially just increased. Subtracting a debt mathematically acts as an addition to your fortune. It makes 10 minus -5 a perfectly logical 15.
And finally, section 5, the Explainer Master Quiz. Time to switch gears from learning to testing. Let's enthusiastically apply everything we've unpacked about real numbers today and see how well you can navigate the number line.
Here we go. Question 5. The absolute easiest way to spot the difference between a rational and an irrational number is just by looking at their decimal expansion. Consider these two numbers, 0.33333, repeating infinitely, versus 1.01, 001, 0001, 00001, just expanding on and on. One repeats a single block continuously, while the other's pattern grows wider without actually repeating itself perfectly. How would you classify them? 0.333 repeating? That's a rational decimal. Rational numbers, when you divide them out, will either terminate perfectly, like 0.15, or they'll repeat a cyclic pattern forever. But numbers like 1.01001, expanding endlessly, or pi, or the square root of 2, those are irrational. They continue infinitely with absolutely 0 repeating cyclic blocks, and they basically fill in the microscopic gaps between our dense rational fractions. The real numbers unite both of these perfectly into one beautifully continuous number line. But what if you run into an impossible problem, like trying to find the square root of a -1? Does the fact that it literally cannot exist on a real number line mean there is an entire other dimension of numbers out there just waiting to be discovered? Well, you'll just have to keep exploring to find out.